Welcome to the Walton Pie. Today we're going to be talking about the squeeze theorem. I like to call the squeeze theorem the Goldilocks of limits because it's not too high, not too low, it's just right. And I think you'll see why I say that in a little bit. So the intuitive idea of the squeeze theorem is the squeeze theorem is a formal way to describe something that feels rather intuitive. So if f is less than or equal to g is less than or equal to h, and we know that f is equal to h, then that tells us that f equals g equals h. So this is something that's going to be true for constants or for scalars, and the squeeze theorem says that this also is going to work if we're dealing with limits. So the formal statement of the squeeze theorem says that if f of x is less than or equal to g of x is less than or equal to h of x for all x except potentially at a, and if we also know that the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x, and both of those are equal to some value L, then the limit as x approaches a of g of x is also going to be equal to L. In other words, we've squeezed g to have to be between f and h, and if they both go to the same limit, then g also will go to the same limit. So for example, a common example of this is, what is the limit as x approaches 0 of x squared sine of 1 over x? Well, we know that x squared sine of 1 over x is always between negative x squared and positive x squared, because sine is always between negative 1 and 1. So that tells us that we can look at the limit as x goes to 0 of x squared, and the limit as x goes to 0 of negative x squared. Since both of those are 0, that tells us that the limit as x goes to 0 of x squared sine of 1 over x is also equal to 0. Now the graph of this is something that looks like it goes to 0, but behaves so weirdly we can't do it using our other standard limit laws. Now let's go through the proof of the squeeze theorem. So, if we know that the limit as x goes to a of f of x is equal to the limit as x goes to a of h of x is equal to L, that tells us that for any epsilon greater than 0, there exists some delta greater than 0, where if 0 is less than the absolute value of x minus a is less than delta, then f of x is in some epsilon ball. So the absolute value of f of x minus L is less than epsilon, and also absolute value of h of x is minus L is also less than epsilon. That tells us that L minus epsilon is smaller than f of x, which is also smaller than L plus epsilon. And the same thing holds for h of x. So, since f of x is always less than or equal to g of x is always less than or equal to h of x, we can squeeze g of x in between L minus epsilon and L plus epsilon as well, which tells us the exact same thing that we needed to have. We then get the absolute value of g of x minus L is also less than epsilon, which tells us that the limit as x goes to a of g of x is equal to our limit L. I hope this was helpful. Please check out my next video where we'll go through some examples of the squeeze theorem as well as looking at the graphs of these functions. Please check out some of my other videos, and please like and subscribe if you have not already, as it helps me to be able to continue to make these sorts of videos. Best of luck with all of your math, and I hope you have a great day.